Good afternoon to everyone, depending where you are. So I'm very pleased today to introduce Professor Alois Pichler as our distinguished speaker in today's Stochastic Programming Seminar, online seminar series. So just very, Alois is a professor in the Faculty of Mathematics at the Technical University of Chemnitz. And he is a long-term contributor to very relevant topics in stochastic optimization. And then I would like to mention he did his PhD under Georg Flug supervision before spending a period as a postdoc in Trondheim, and then before joining Chemnitz University for his academic career. And Alois is well known for work in probability theory and stochastic optimization, but in particular, he published a very relevant textbook on multi-state stochastic optimization in 2014 with Georg Flug, which is widely adopted also as a reference textbook in our courses. And he's associate editor of Mathematical Programming and SciEM Review, and is also editor of Mathematical Finance, which brings me to say that actually Alois started his career in the banking sector, and has therefore quite extended knowledge on financial markets and insurance markets, which is an area to which he has contributed over the years. So he was member, actually, if I'm not mistaken, of the COSP committee just before us, pretty recently, and he's also has been member of the Euro Working Group Stochastic Optimization Management Board over the years. So today he will be present, and I'm pretty interested. He will be present a topic which is very relevant over the years, stochastic dominance with applications in stochastic optimization. So which is an area that is also of great interest to me. So Alois, welcome, and please, the floor is yours.
Okay, thank you very much, Giorgio, and thank you very much to the entire community for the society for inviting me, for having me here today. As you just has announced, I will talk about stochastic dominance, which is where I did some papers on these topics, where I returned back because of interest. But I do have some other topics as well where I do my publications. So I'm going to talk about stochastic dominance. I'm going to introduce that first, and will talk about order 1 and order 0 stochastic dominance first. And I will try to extend this to some higher order stochastic dominance, what we did there actually last year or the last 2 years, because I think that we have understood here something what is going on, what was not so clear in the years before. And that's the reason why I try to work on that. So let me start with this small introduction here first, just to have everybody on the page. By the way, when you introduced me, Giorgio, I scanned the participants and I saw that there are many well-known faces. So hello to all. I don't want to greet them in person, but hello. Okay, so the idea in general stochastic optimization is that we would minimize some objective function, and one of the very oldest problems is the Markowitz problem, which minimizes the variance. I hope you can see my cursor, I'm not sure. And there's a constraint, which is the expected value constraint, to achieve some minimum return. This is what we usually call the budget constraint. And this is the no short-selling constraint if these parameters are to be non-positive, actually. So this is one possible way of stating this. And the other possible way of stating the problem is this here, as I have it on the right-hand side, on this dual, where we maximize the expected value and where we want the variance not to exceed a certain threshold. So this is just the second possibility here. A typical robust optimization problem would look in this way, that we minimize on X some maximum. The xi here is the random component. The xi can range in this capital Xi here, and the robust optimization problem would minimize in some parameter with respect to a maximum. So this is a min-max gain, which is very well known in game theory. And the constraint could be a robust constraint as well. I will talk about utilities because this fits nicely. For utilities, there would be, in addition, a utility function u here, expectation of u of something here. Well, if the problem is simple risk-averse stochastic problem, we would have some risk measure very often involved here, which is a summary statistics. So there's a random variable, this q of x and xi. As I have mentioned, x is a parameter and xi is the random component, the random variable. So in total, this is a random variable, and the risk measure would just summarize these random variables in a real number. So that would be risk averse, but what we are going to do today is this type of optimization problem, which is this here. We minimize something, for example, an expected value of a utility, as I wrote that here, subject to this random variable now should be higher, should be larger than some reference measure. So a typical situation would be that you are an investor, you want to maximize your profit, subject to that the portfolio which you are building should in some way be larger or in some way dominate a reference portfolio, for example, an MSCI ETF or the Dow Jones or whatever this is for you. So this would be the problem setting. What is this? So which types of stochastic orders should we involve here? The simplest stochastic order is this here. If x and y are two random variables, then we can say that x is smaller than y in some everywhere order if x is always smaller than y. So irrespective of the realization of x, and if you observe both realizations, x and y, x would be smaller than y. So this can be true. This would be the typical everywhere realization, but this is deterministic. It's not really random. There are no random components involved here, except this omega here, which is the random variable, the realization in this space. So to put it in a more realistic, probabilistic setting, we replace this everywhere by almost everywhere, and this is what usually people would denote as stochastic dominance of order 0. X is smaller than y if x is smaller than y with probability 1. So you still can think about this to be in a way deterministic because you just would consider or encounter all realizations and compare these realizations. So this is the usual 0-order stochastic dominance. The first-order stochastic dominance is here. X is smaller than y in first-order stochastic dominance if the expected value of u of x, so here we involve utility functions, if the expected value of u of x is smaller than the expected value of u of y. So x has smaller utility than y, and here we consider all non-decreasing utility functions. This would be a definition for that. On the right-hand side, something what comes naturally with that is to define the CDF, the cumulative distribution function, as the probability of this x to not exceed this small x here. Of course, we can rewrite this here as an expected value of everything up to this x here. And then there's a characterization, and this characterization is this here, that x is smaller y in this first-order stochastic dominance if the CDF, the first CDF is larger than the second CDF. So x is smaller than y if the CDF is larger than the y because it has higher probability. This is what we would think about that. Or there's an equivalent relation if we involve the inverse. So if we invert the CDF, the inverse is the value at risk, and the value at risk as well can be stated in this way. The value at risk of x is smaller than the value at risk of y for all y's. So this first comparison was for all x's. This other comparison is for all alpha levels alpha. If this holds true, then those random variables x and y, they are in this relation, in this first order stochastic dominance relation. So it's not any longer an almost true relation, but it is just a relation which involves those utilities or those probabilities, those observations. And the typical problem would look like something like that. Maximize some expected value of x subject to the x, so the candidate x, is larger in first order stochastic dominance than the reference. This would be the usual problem. The difficulty with that is that this set of all random variables which dominate x, this set is not convex, and this set is not convex neither. The second set is those random variables which are dominated. So the first are the random variables which dominate x. These are the random variables which are dominated, and neither of them is actually a convex set. And this is where we do have some difficulties in stochastic optimization. But in general, we could even try to solve that despite the fact that it's not convex. And the problem basically looks like that: maximize or minimize in x here. And the maximum where we have to look at it is the max. We have to compare those CDFs of x and the reference x in order to just find a feasible solution, because already finding a feasible solution for this problem here is not a trivial task. So because it is not convex, the feasible solutions are not connected. And well, even to find a feasible solution could be a challenge, and it is what it looks like. So for example, to solve this problem, once we find an x, a random variable, so that this maximum here is smaller or equal to 0, then we at least have found a feasible solution. And in this feasible set here, in this set of feasible solutions, we could try to find the real, perhaps global or perhaps local solution. So sometimes it is, of course, desirable to replace this t, which is the t on all reals, only by a finite number of t's. And this is, of course, something you would be interested in usually whenever we are doing stochastic optimization. We could consider alternatively this problem here, minimizing x and the maximum on alpha. So instead of having a look on the CDF, we could have a look on the inverse of the CDF, which is the value trace. This would be a similar problem, just to find a feasible solution of this problem. I had a colleague here from Ukraine recently in the last year, and he has been working on that, and here's just the usual set of feasible solutions, or set of solutions for the problem, for the very initial problem, which was published or which was used by Markowitz. That this problem had a couple of dimensions. I think it was just 6, not very high dimensional, of course. And here are what you see here is the projection to 2 components only. And these are the feasible regions. So what you should realize is that the feasible regions of this simple problem where stochastic dominance of first order is involved, they are somehow weird. They are not connected, and they are difficult to find in many situations. So this is what these 3 pictures actually should convey you. There's another possibility how to solve these optimization problems, at least for first order stochastic dominance, by considering some objective function, and this g function is the maximum, which you have seen earlier, which I have introduced on this earlier slide, which is the maximum of all candidate t's, which have to be tested. So if this constant here is large, then it is actually possible to somehow connect the non-feasible region with the feasible region and try to simply work everywhere. This would be the idea here, which I want to present. And using this mollifier, this function is called a mollifier here. This psi or psi theta this is the usual Gaussian distribution, we can use this modifier psi's here in order to just compute this convolution. So what this modifier is doing, it is just making a convolution out of the initial function. The new function would be f theta, depending on this parameter, in order to smooth out this function. And the idea would be to use a stochastic gradient method to just walk around everywhere, the non-feasible region and the feasible region, and to just find the maximum. If it's not feasible, which is this case here, if it's not feasible, then the result would be small if we choose C just appropriate. And if it is feasible, then we could have our usual objective function. That's the idea. And why do we do that? Because of Stein's lemma. Stein's lemma actually allows us, if X is a normal distribution, it allows us to compute the expected value of the gradient just to be computed as the expected value of the initial function times this X minus mu. So they have the same expectation, and the idea of this Stein's lemma is just to exploit this relationship here in order to compute the expected value of the gradient, because we want to have the gradient to tends to 0 if we want to solve this problem. Well, Stein's lemma itself is a simple consequence, because we have for the usual Gaussian distribution that phi prime is minus z and phi times phi, and if you then do multiplication by parts, you simply will get this Stein's lemma, even in higher dimension. It works in higher dimensions as well. And here is a solution to that. What you see here in those charts, these are non-feasible regions, which are the small ones, and the feasible regions are the other ones. So what we do here is we start somewhere, we climb the non-feasible region, we suddenly find a feasible point where everything would change, and then we do this, we continue optimization in this region by letting this parameter, this modifier, tend to 0 as well. So this is just the message that it is very cumbersome. There's very computational intensive to do this type of computations, but it is possible to run stochastic dominance of order 1, even on, well, some reasonable dimensions, if the dimension is not too large. So that is possible, and these are the proof for that, again, where we just start somewhere and then find the feasible region and continue in the feasible region to find an optimal point, or at least a point where we could be happy with, a local optimum in many situations. Okay, there's another possibility, because here we are dealing in a kind of optimization problem with nonlinear constraints, basically, and the nonlinear optimization problem itself, and the projective exact penalty method would be a different method in order to manage that. And we have tested that, and it works as well. So what is this? If you want to solve this optimization problem to minimize a function subject to a feasibility constraint, then you can rephrase it in the right-hand side, and that's the idea of this projective exact penalty method. Pi is a projection which projects any point into the feasible region. So once you are in the feasible region, then pi of x would be x. So you would not jump out of this feasible region. But if you are out of this feasible region, this projection would project into the feasible region. If this is a convex domain, then one could do this here, just compute the arc minimum, find the smallest point in the convex set, in the feasible set. And this is a projection, of course, again, a nonlinear projection, but this even works on star-shaped domains. So this is a star-shaped domain here, this green here. The x0 is in the center of the star, and all rays are in the star. So along those rays, it is possible to find the first point, which is in this area, and then you would just continue this computation. This is what this function pi does here. So f of pi of x is, you would always evaluate in the feasible region, But if you're outside the feasible region, then there's a penalty which drags you into this feasible region. So it's a very simple approach here, but it's very unusual. And what I want to say is that this can be used for stochastic dominance of this first order as well. And we tested this to some extent. Okay, let me continue now to second and higher order stochastic dominance, because we have been doing some work specifically on higher stochastic dominance relations. What is that? So the second order stochastic dominance relation is this here. We say that X is smaller than Y in this second order stochastic dominance if the expected value of U of X is smaller than the expected value of U of Y. So if we again use utility functions here, so X has smaller utility than Y here, but the utilities we use are non-decreasing functions and concave functions. This is what typical utilities would look like for an individual person, for an investor. They are concave because, well, if you are getting richer, you're getting perhaps a little bit happier, but not too much happier. That's the usual economic interpretation or behavioral interpretation behind that. Why to use non-decreasing and concave? But what is new is this concave in comparison to first order stochastic dominance. And they can be characterized as well. Here are some characterizations. So this is equivalent that we had that for the first order stochastic dominance. We had a comparison of CDFs. This is what we have here as well. But here it's a comparison of integrated CDFs. This is a second comparison. We had for the first order stochastic dominance a comparison of value at risk, so the inverse CDFs. And here we have something which is again similar. It's the integrated ones. And here is the average value at risk. It can be used with the average value at risk as well. And the constraint is this here: minus average value at risk of minus X is smaller or equal the same object of Y for all levels of alpha. So that's the idea. We need to compare again of all levels of alpha, which are infinitely many, right? It's uncountably many points which we need to compare in order to make sure that a stochastic dominance relation would hold true, even for the second order stochastic dominance. So there are always uncountably many constraints involved here. I have the average value at risk defined here. Actually, I cannot see it on my laptop right now because there's the bar of Zoom, which it doesn't seem that I cannot remove it. No, it did. Okay, it's the usual definition, of course, where we consider the right hand, the upper part, 1 over 1 minus alpha of this integral here. And so here you see why this comes naturally, because this is the integral of the value at risk, which is the same here as this integral here, the integral of this is the value at risk as well. So that's the reason why this comes naturally here for all levels of alpha, why this comparison actually holds true. Okay, this means that the average value at risk came in here naturally. I think I do not have to repeat those usual axioms which we have for risk measures, because we will use other ones as well now. So this is the usual monotonicity axiom, where a risk measure of X is smaller than a risk measure of Y. This is the property of a risk measure. The average value at risk is one of those risk measures. We do have this homogeneity, we do have this cache invariance, and we in particular have this convexity. And this is why, why the second order stochastic dominance turns out to be much more handy than first order stochastic dominance. Here are some usual risk measures, the risk neutral and the risk averse one. But the main point which I want to make is here that this average value at risk has this additional formula where at least 3 people claim that they had found this formula. It's a minimum, again, the minimum representation. Actually, that should be Y. I just realized it should be Y. I wrote average value of Y, but then switch to X, I'm sorry. That should be Y everywhere. So this is the usual minimum representation. Actually, it's a dual representation because you can dualize what is going on here. Just linear dualization, and this is the problem you would end up with. Why do we have this strange minus of minus? And this actually matters. So it's not the same. This is not the same as average value at risk of alpha, even if you would change the alpha to 1 minus alpha. This is not the same in general. Well, the situation is this here. If there's a certain distribution, here is 0, here is the expected value of y. And if the realization is on the right-hand side, it's a profit. If the realization is on the left-hand side, it's a loss. The value at risk, the 5% value at risk would be this here. But we have defined this average value at risk on the other side, on the positive side, actually. So if we flip this everything, and this is just flipped from X or Y to minus Y, then the expected value flips on that side, and this tail flips on the other side. So this value at risk here is then the 90% value at risk in this case, not in general. If the distribution is a non-continuous distribution, if that is discrete, then this is differs. But the average value at risk is this guy up here. So this is the 95% value at risk, and the corresponding 5% value at risk is this down here. So this is the point which I want to make, that we need to take care. Is this risk measure now in order to generate the profit, or is it to take care about losses? And we use it here as a constraint, which means to minimize losses. So we need to care about the left-hand side. And that's the reason why we just have to care about the orientation of the distribution. That's not the same. Okay. And here is another point, which is, I think, important. The order is not connected, so this is not a total order. Actually, it holds very often, if you just took random observations from some stock exchange, it's very often true that X is not dominated by Y and Y is not dominated by X. So we know from relations, X is smaller than Y, that either X is smaller Y or X is larger than Y, or they are equal. This is at least for the numbers, as we know that, but this is not true for general random variables, not even for this second order stochastic dominance. The only thing what is true is this here. This set is a convex set. So those Y's, those strategies which dominate X, this is a convex set. The other set, which I have mentioned earlier, so the Y's which are dominated, this is not a convex set neither. But this set is a convex set, and this is important. So, because of this observation, it is actually important if you do stochastic optimization or portfolio optimization with these types of constraints, you somehow need to be aware that this happens very often, that random variables are not comparable. So you might end up, even in this situation, in this very simple problem statement as it is given here, that you would not find feasible solutions. So the problem is here, expected value of X transpose psi, which means a usual profit optimization here, subject to the portfolio which we are building, X transpose psi, should dominate a reference portfolio. So this is the reference portfolio. Here is the usual budget constraint and the short selling constraint here as well. But in order to ensure that there are feasible solutions, actually Dencheva and Kruczynski, they have come up with this setting here to add something, which means to give up on some return, which is the C here, but on the contrary, to penalize here the objective with respect to that here. So if you do this, then you would at least ensure that you would always have a feasible solution. But however, you might still not be able to beat this benchmark which is given here. But at least you would find a feasible solution, and hopefully a good feasible solution. So this is what these authors came up with. So higher orders. because many people have been working on these stochastic dominance of lower orders. So first of all, there are integer orders. And the integer orders, they are naturally defined. We have seen earlier that we have compared the CDF or the integrated CDF. And for integer orders, you would just continue integrating the CDFs. This is what is here. So the indicator K here is just how often you iterate this integral here. And then you would get a weaker and weaker stochastic order. And you can still define what does it mean for X to be smaller than Y in this smaller or weaker stochastic order. So that's the idea, to weaken this order because stochastic dominance of first order is terrible. It's not convex and difficult to obtain. Second order is again difficult to achieve, but at least it is convex. These stochastic orders, they are difficult as well, but at least they are slightly weaker. That's the reason why people have investigated that. And this is the definition they came up with. This is equivalent, again, to compare expected values. Expected values of q minus x to some power k, so the positive part, q minus x to some power k, or k minus 1. This needs to be compared with expected value of q minus y for all q's. But still, we do have those infinity many constraints in order to deal with these integer higher stochastic orders. This can be extended to non-integer by just picking up the formula which I have just mentioned earlier. For a general real p, it should be larger than 1. We can say that x is smaller than y, or y is dominated by x, if now we pick up this formula from the earlier slide, the expected value of q minus x with this power involved here is larger than the corresponding quantity for this y variable, but still for infinity many constraints here. So for this, actually, we have found a characterization. And the characterization we came up with is that it is possible to characterize this higher stochastic order of any integer order here by involving risk measures again. And the risk measure again is this higher order risk measure. It's defined in the very similar way as this average value at risk, but involves a different norm here. It involves the Hölder norm, the Hölder p minus 1 norm here, and it defines a risk measure. It's a risk measure in the sense I have mentioned that earlier. And the characterization is this here, that x is dominated by y. Instead of having these relations, we can compare the risk measures or evaluate the risk measures at different risk levels. So r of minus x is smaller than r of minus y of this higher order risk measure for all risk levels beta. If that holds true, this characterizes the stochastic dominance relation as well. So this means that we link here stochastic dominance relations with risk measures in a almost one-to-one way. Well, what did we achieve now? At least we have a comparison. But whenever we will do computations with these constraints, we still have the problem that we need to verify this constraint here for all t's, for infinity or uncountably many constraints t here. And of course, we do not want to handle this. And it turns out that there's a strategy to avoid that. We can reduce, it's possible to reduce this infinity many constraints here to only finitely many, because there is a characterization of those t's which really matter. And the characterization is this here, that we can have a look on the derivative. If the derivative of this corresponding function, if they coincide, I will have a picture to illustrate that later. If the derivative of those objectives here, if they coincide at some point t, these are the important t's. So you can forget all others. It is sufficient to just find those t's where the derivatives coincide, and then compare, then have this comparison for only those t's, which means that's a possibility to reduce those infinity many constraints to only finitely many And this is the illustration. So here is the blue line, which is this expected value, which is the norm basically of t minus x. And there's this red line of t minus y. We need to make sure that the bold red line is below the bold blue line. This is what we need to make sure. So let's have a look at the derivative. It is not possible that they would intersect like that. Because if they intersect like that, then one would shoot about the other and the constraint would not be satisfied. It is actually necessary that they touch. Touching means that they have the same derivative at that point. And this is what you can see here. The dashed lines are the derivatives. So the dashed blue line is the derivative of the blue, and the dashed red line is the derivative of the red line. And here the derivatives match because those 2 points touch. Here is another point where those 2 points touch because the derivatives match. They are the same at this point. And it is sufficient to test only these boundary points here of these blue areas and the red areas. Actually, it turns out that even less, only the right point here of this blue area, red area, or the left point of this blue area is a point which is of interest. So this enables us to reduce the infinity many constraints to finitely many constraints, but of course at the cost to compute this derivative here and to somehow manage this derivative here. How can this be done computationally? So from computational perspective, this is the function. It's expected value of t minus x transpose psi minus the reference. This is the function. We can compute, and this is the positive message, we can compute the derivative of this function explicitly. It's this guy here. And it's basically the same function as above with p minus 1 here times psi. So it's an inner product of this original function with a different exponent here times psi. Yeah, and here I have stated the problem again now. If we want to minimize this problem here, subject to these constraints here, to stochastic dominance constraints here of some order p, well, then we can do the same here by just having a look at this function. This is the function, and involving its derivatives here. So this is the reformulation. Minimize only those random variables for which the g of those points is smaller than 0, smaller or equal to 0, which satisfy this constraint here. So this is an equality constraint. If this is satisfied, then we need to make sure that the g is smaller. So that's the point here. There's a kind of if condition in the constraints, but nonetheless, this reduces the number of test points to a finite number, and that's the main advancement in checking these constraints here, those stochastic dominance constraints here. Well, when it comes to implementing that here, we have this function g bar. This is the function which I just have mentioned. If the derivative is 0, then the function needs to be smaller or equal to 0. That's the constraint here. So this means that we have an optimization problem, and the inner problem is an optimization problem itself. And the inner problem is a nonlinear optimization problem. And this t, where this maximum actually is attained, defines, this is the optimizer, does depend on this x here. So for this reason, we can involve the implicit function theorem and compute even this gradient of this function g bar here, because again, it is defined itself as an optimization problem, and it has an inner function, and with the inner implicit function theorem, we are in the position to compute the derivative, at least if everything is regular and stuff like that. Yeah, this is what the Lagrangian does look like. To apply Newton's procedure. It is straightforward. So the first part is the simple objective. Then there is this other constraint, which is the budget constraint. These are the short selling constraint here. And this is the crucial constraint here, which is the non-linear part, which comes in addition, which makes sure that we would satisfy stochastic dominance here. This is the function g, which I have introduced in this earlier slide here. There are some derivatives, of course, involved here. But again, the important point here is, so the first derivatives, they are all standard. But we get something in addition that we need to make sure that this function where those points touch, that the function values are the same and the derivatives are the same as well. So they touch first of all, but this could be like that as well. But to make sure that the touching point is smooth, we have to make sure that the second holds as well. So these are those two constraints which come here in addition. First of all, touching point. Second one, it is not something, so they do not intersect those points, but they really touch. So this is the other point. But nonetheless, this is a very non-linear optimization problem because those components t and x both, they appear here in a nonlinear way. And that's the reason why we involve Newton's procedure here in order to get that solved. Here's an example. We did this actually, where we have used 6 stocks. These are the 6 stocks. We did this computation some months ago. That was before Trump was president. So there was, of course, an impact on those stocks, but not visible on these pictures. So these are the 6 stocks which are used in, which are the highest stocks in the MSCI World Index. That's the reason why we have used them, and we just wanted to realize what is going on. And here is the results. So we did a portfolio optimization exercise now of order 2, 3, 9, 10, 15, 20, and so on. And so this is the objective, which goes up here. And this is the investment strategy we would see here. So as a result, we would get for higher order stochastic dominance if the order increases. So again, recall if the order increases, then the constraint is getting weaker and weaker, not really weak, but weaker. And this leads to the fact that we would intend to invest in one single stock, the stock which has the highest return. And in this window, which we have considered here, NVIDIA had the highest return. That's the reason why we just would see NVIDIA here, and then Apple and Microsoft as the other ones. So that's the general observation, which is, I think, very much in line with the expectations, what stochastic dominance could do and how stochastic dominance would treat the problem. So in general, we're getting better than the MSCI World, of course, because we are going into investments which have been better in this region, in this area, but at the cost of more risk. And the risk is in this respect that we tend to invest in single opportunities here. I have mentioned that there is a dual characterization which involves risk measures. And the characterization which I've mentioned is this here. X is bounded by Y in this p-order stochastic dominance if this inequality for the risk measures is satisfied for all risk levels of beta. And here as well, it turns out that it is not necessary to test all betas, because again, these are infinitely many in the interval 0, 1, but it's possible to reduce them to a finite number of risk levels, beta I here, which are crucial. And the question is, can we somehow find those risk levels which are crucial, and how can we identify those risk measures? And it turns out this is true. So this here is the risk functional again, or the risk measure, but how can we characterize those betas which turn out to be relevant in contrast to the other ones? So we want to reduce this infinity many beta to only finitely many beta, and the question is, which are these? So again, this is a picture of this function R beta. So this is the risk measure, the blue one of X, and the red one is the risk measure of Y. And this is the optimizer. So let me recall, here we do an optimization procedure. That's an infinite. And there's this is at least for each beta, this is achieved at some t. And this is what is plotted here in this other picture. This is the optimizer. The optimizer, depending on beta, so beta is below here, the optimizer, depending on beta, is this red curve, and the other one is this blue curve. And again, it is the case if those two intersect, these are the critical betas. If the optimizer intersect, then we need to investigate those corresponding betas. This is the result of what we have found, how to characterize, how to reduce those uncountably many constraints to only finitely many. So that's the criteria. So can this be somehow extended to non-scalar orders? Yes, it can. Because we have seen earlier, we had stochastic dominance of order 1, of order 2, of integer order and higher orders. But actually what matters is just that we have involved a norm. We can say that x is smaller than y in some stochastic order if we have a norm. If the norm of q minus x, its positive part, is larger than its q minus y, this should be y, of this positive part here. This is an equivalent comparison, but it is not the stochastic dominance of some scalar order. It does not depend on the scalar. It is actually a norm. And the characterization here is this again. It's possible to characterize this stochastic dominance relation by involving just a new risk measure, which does not involve a Hölder norm, but involves just any norm. It doesn't matter which type of norm that is, just take any norm, and then you can define a stochastic dominance relation. That's the idea here. Okay, yeah, so this is kind of concluding remark here. Every norm defines a stochastic dominance relation. Every norm defines a higher order risk measure, and every risk measure characterizes the corresponding stochastic dominance relation. So that's the main message which I want to give here, that it is indeed possible to extend this stuff to non-scalar behavior and to have a generalization of stochastic constraints. I have seen, just as another concluding remark, I have seen that there are variants in 2- and multi-stage optimization. Maccioni and my supervisor Pflug have been working on that. I should mention as well that there are many papers on second-order stochastic dominance by Ruszczynski and Dencheva. They have somehow coined the field, especially for second-order stochastic dominance. They have found possibilities to reduce this to finitely many points in case of discrete measures. So our situation is more general. It allows to find only finitely many points, even if it's non-discrete or continuous, and if it is higher stochastic order. So that this is everything possible. This is what we cover in this paper now. Okay, and basically that's it. I have added here a couple of papers which I was referring to in this presentation. A few of them are mine, but I already have mentioned that Dencheva and Ruszczynski, Ogrychak, for example, have been working on that as well. So this is what I have prepared. Thank you very much for your attention here.
Thank you very much.